You'll be happy to know that this section is actually a relatively short section. It primarily consists of learning to recognize different types of shapes in 3 dimensions. So while the pages of the lecture notes may be long, that's mostly because there are lots of pictures. There's not actually a lot of calculation that takes place in this particular section. What we want to talk about here are different types of shapes that can occur in 3 dimensions. Now, we've talked about lines and vectors, we've talked about planes, and we also talked about equations for spheres. We want to extend our repertoire of different 3-dimensional surfaces to include what are known as cylinders and quadric surfaces. Now, cylinders are things that are created by what are called rulings. Rulings are sets of parallel lines. And it's sort of like taking a shape in a 2-dimensional space, say a parabola, so you have a parabola, and then pulling that parabola along a line parallel maybe to one of the coordinate axes or some other line. So if you pull that parabola along that line, you get sort of this, well, it looks like a half pipe if you like to snowboard, right? So you have this parabola shape being pulled along a line. Now, these lines are all parallel to the line you're pulling it along, and those are called the rulings. So this is what we mean when we talk about a cylinder in 3-dimensional shape. Now, a quadric surface is something slightly different. A quadric surface has to be a surface whose form can be written like this. Now, this looks enormously complicated, but basically you have an x squared term, y squared term, z squared term, or the product with x with y, or x with z, or y with z, or x by itself, y by itself, z by itself, and maybe a constant. Now, in quadric surfaces, not all of these terms have to be here. You'll be happy to know that actually the ones we're going to study, they have relatively few terms, generally around 3, maybe 4. So you're not going to see all of these terms present at any given time, but it can be written in this form. If it can be written in this form, it's what's called a quadric surface. And that's sort of coming related to the quadratic formula, where the highest degree in the variables is 2. So if we have something with x cubed, it may be a surface, but it's not a quadric surface. Now, there are some cylinders that are quadric surfaces, and there are cylinders that are not quadric surfaces. Let me go ahead and share my screen with you, and we'll get started looking at these fascinating surfaces in 3 dimensions. We're going to start again with a discussion of cylinders. Now, typically a student, when they think of a cylinder, they think of the shape of a Coke can. So what they're really thinking of is something that has a circular base, and then all of the cross sections are circles of the same size and same shape, and that it's at a right angle to the base, which is the circle. That's what we typically have students thinking of when someone says the word cylinder. It's actually a right circular cylinder, right meaning that the base is perpendicular to the length along which it's symmetric, and that the base of it is a circle, so all the cross sections are the same. This is a cylinder in the mathematics sense, of course, but there are other things that count as cylinders that do not have this right circular cylindrical shape. Let's take a look at these. These are created by sets of parallel lines, which are called rulings. Now, the ones that are the rulings in this picture right here are the ones that are parallel to the z-axis. If you will, visualize a circle in the xy plane, so the floor. So you're looking down, you have this circle, and you grab the circle and you pull it up like a slinky, right? You're creating a 3-dimensional surface, and that will create something like this right circular cylinder. And you're pulling it along lines that are parallel to the z-axis. And because they're parallel to the z-axis, then these are called rulings, and they're not showing up very well. Let's see if I can make them a different color, if they show up better. Well, they're still not showing up great, but basically the rulings that you see here are the lines that are parallel to the axis along which you're drawing that 2-dimensional shape. These lines are called rulings. Now, when we look at it, it doesn't have to be a circle. So it's still considered a cylinder if the basic shape is not a circle. So let's take a look at these two right here, which are in fact cylinders in the mathematics sense. This one right here is created by a cubic equation. So z equals x cubed. Because it's cubed, it's definitely not a quadric surface because the highest degree on a variable in a quadric surface is 2. So it's not a quadric surface, but it's a cylinder because we've taken the shape of this cubic equation, z equals x cubed in the xz plane, and we've drawn it along lines that are parallel to the y-axis. And these become our rulings. So let me go ahead and highlight some of these rulings that we have right here. And notice they're all parallel to the y-axis right there. So we've taken a two-dimensional shape, a cubic, which, kind of looks like that, and we've drawn it along a line, and it's creating a three-dimensional surface. Now, this is fundamentally different from the right circular cylinder in that this is not a closed shape, right? It doesn't enclose an area completely. It's open. This one over here to the side is the equation x squared minus y squared equals 2. Now, this is a quadric surface. So when we're looking at this one, because it does fit the equation that we gave earlier, the highest degree on x or y is 2 with coefficients and a constant involved. And it looks sort of like this right here. Now, because it mentions x and y in the equation, then the variable that's missing is the one that is being pulled parallel to. So this is actually the graph of a hyperbola in the xy plane, and it's being pulled parallel to the z-axis. So the rulings are the lines that are parallel to the z-axis. Let me show these here in white. So these are the rulings right here, which are parallel to the z-axis. Well, that didn't work out too well. I kind of knocked out my entire z-axis, so parallel to the z-axis, which is right there. Let's go ahead and take a look at this one. This is based on a hyperbola. So you can see this right here. Now, how can you tell that it's really a hyperbola being drawn along the line? Well, let's talk about how to manipulate things in CalPlot 3D. If you want the typical view where z is up and x and y are kind of splitting the space in front of you, hit the home key on your computer. If your computer doesn't have a home key, use the function key and the left arrow key, and that will give you the typical view with the z up and the x and y splitting the distance. In this case, this doesn't help me. This isn't the view I want. I want to view what it looks like in the plane, specifically in the xy plane, because I pulled it parallel to the z. So in this case, I want to do an Alt-Z. When you hold down the Alt key and hit the Z key, it's going to give you the XY plane where the Z is coming out, in this case, directly towards you. And you can see the hyperbola that it's based on. And again, it's a little off because CalPlot 3D is trying to make it look three-dimensional. It's really just exactly a hyperbola. And then we're pulling this entire graph along lines that are parallel to the z-axis, and it's creating this three-dimensional shape, and I'm going to rotate it off, that you see right here, right? And it continues in both directions, of course, forever. It's also not a closed shape, but it is a quadric surface. Now, open curves, such as cubics and hyperbolas, don't enclose them. But if we have something where the basic two-dimensional shape is a circle or an ellipse, it will completely enclose a space. So the typical right circular cylinder and the elliptical cylinder, which you see here below left, are examples of closed curves. The one we just saw, the hyperbola and the cubic, those are open curves. So let's take a look at these two right here in CalPlot 3D. So this one is the equation of x squared divided by 2 plus y squared divided by 2/5 equal 1, which is the basic equation for an ellipse in the xy plane. It doesn't mention z, so it's being pulled parallel to z. So let's come over here and take a look at that one real fast. So let me close up that hyperbolic one. Now you may wonder, well, how can I get rid of that box? That box is bothering me. Simply click somewhere in the open space where the graph is, and then hit the B key. That will toggle it on and off. Now, this one has an equation in terms of X and Y. So again, we want to get rid of the Z. So we're going to do Alt Z. And now, again, given that CalPlot 3D is trying to make it look three-dimensional, you can see the shape of the ellipse on which it is based. Right? And then it's drawing it along lines called rulings that are parallel to the Z-axis. And when you tilt it, you can see those rulings, which are right here going in this view vertical. Now let's go ahead and take a look at the one next to it. The one next to it has equation 5y squared equals z. So it mentions y and it mentions z, but it doesn't mention x. So it must be a graph in the YZ plane that's being pulled along rulings that are parallel to the x-axis. So if I want to get rid of x, I hold down the Alt key and hit X. And now you can see that, well, yes, 5y squared equals z would be the graph of an upward opening parabola in the YZ plane. And then it's being pulled along lines called rulings that are parallel to the x-axis. So these rulings are running this direction. Now let's go ahead and move on to another shape. We've defined what the cylinder is. The cylinder is a sort of two-dimensional shape that's being pulled along sets of parallel lines called rulings, and that creates the cylinder. Now let's talk about what a trace is. We've actually been looking at the trace of the cylinder in a particular plane. So the trace of a surface is the cross section that's created when the surface intersects a plane parallel to one of the coordinate planes or the coordinate plane itself. So the ones that are most important for the cylinder would be the plane that doesn't mention the variable that's creating the rulings. So for example, in the last example, it was in terms of y and z. So the rulings were parallel to x. So we took x out of it and looked at the trace in the YZ plane. So let's talk about how we can get traces. Here's an example of another one. Can you guess what this is based on? Yeah, that's right. It's the sine function. So this is a cylinder which consists of the sine function. It's in the XZ plane, so you can see the graph of it right here. And it truly just is the sine function that's being pulled along lines parallel to the y-axis, and you can see it here in this graph, right? And when we're looking at this, this creates that three-dimensional shape. Now, this one's not closed, and it's not a quadric surface because sine of x can't be written in terms of ax squared plus by squared plus cz squared and so on. It's got trig in it, which is definitely not going to be a quadric surface. So a cylinder does produce traces in all three planes, the xy, the xz, and the yz, but only one set will be useful for graphing the shape of the cylinder, and that would be the one that does not use the axis parallel to the rulings, the shape along which it's being pulled. So in this particular one, the one that we have up here, which is the sine of the function, so we have z equals sine of x. So this is our equation right here, z equals sine x. So let me write that down. So z equals sine of x, right? So y doesn't show up in the equation, so the trace I'm interested in is the one in the xz plane, right? Remember that when we graph in a plane, z always gets to point up, and if it's in the xy, we know that y would be pointing directly up. So the trace we're interested in would be the other one. Now, it does have traces in the other planes. They just don't show us anything useful for the cylinder. Here are some typical shapes for a circular or elliptical cylinder. So remember that a circle is really an ellipse. It's just a special case of an ellipse where the denominators a squared and b squared are the same number, and that would give you a circle. So here's an example of three different types of elliptical cylinders. And the first case, we can see that it mentions X and Y. So the base shape is in the XY plane, so the rulings must be parallel to Z. The second mentions the XZ plane, so the rulings are parallel to Y. And the last one over here mentions the Y and Z, so the rulings are parallel to X. So what does this look like? Now, these would be closed because they're based on an ellipse or circle if a squared and b squared are equal. So these have a tube shape, which would include, well, straws, burritos, pipes, all of those kinds of things, ductwork, right? So those would be your circular or elliptical cylinders. Now, if we look at this one, note that the tube could be other shapes. It's still considered closed. They could be octagonal, which is what we have right here. We have an octagonal cylinder where the base shape is an octagon, and then it's pulled along rulings, in this case, parallel to the z-axis. But if you think about it, a hallway, just a hallway like in college, is itself an example of a cylinder where you've taken a rectangle and pulled it along some line. And so you can think of a hallway as a rectangular cylinder, and it is a closed shape. Let's go ahead and take a look at this one down here in example 1. You can see the picture in GeoGebra 3D, which is here, and I've graphed it for you in CalcPlot 3D as well. And again, you can see here that it does produce a shape. It would continue in all directions. It's just CalcPlot 3D. It's only graphing what it sees. And we can see that the rulings must be parallel to the z-axis. So if I do Alt-Z, I should see the ellipse on which this one is based. And now let's take a look at the next example. So we're basically going through lots of examples here. This one, of course, is a circular ellipse. X squared plus y squared equals 9. So basically between -3 and 3. And the rulings are parallel to the z-axis, right? Now, this is an example of one that is a parabolic cylinder. So I have it graphed in both GeoGebra 3D and CalcPlot 3D. And when you're looking at this one, you can see these here. And if I'm remembering correctly, blue is Z, red is X, and green is Y. I don't know why GeoGebra doesn't label them. That would be far better rather than just color coding them because, well, obviously red and green is a terrible combination, right? Some people are colorblind. So you can see that this one is based on a parabola. It's kind of hard when I go exactly head on, it almost loses the parabola, but you can see the parabola shape that it's being drawn along. And then I graphed the same thing in CalcPlot 3D, which you can see here. The rulings are parallel to the z-axis. So if I do Alt-Z, I should see, it's a little skewed, but I can kind of see, well, no, that didn't work. Let's see, nope, that didn't work. Yes, well, the best you can do. You can see the parabola on which it's based, and then it's pulled along the z-axis. All right, so let's take a look at another example of one. We want to go back to the cylinder that was z equal to x cubed. So we have z equal x cubed, which produces a cubic equation in the xz plane. So this is the xz plane. And then when you pull it along rulings parallel to the y-axis, you get, well, it kind of reminds me of a piece of bacon, right? So it's got this nice little shape to it, but it's not closed and it's not a quadric surface. So when we look at this one, and I think about what a cylinder does, I try to visualize what that cross-section shape looks like in the plane, the 2D shape. And then I sort of draw it up like a slinky or like it's a collapsed piece of fabric and I'm pulling it up along it. So I'm creating like this curtain wall along the third dimension, the one not mentioned in the equation. Now, it is possible to have a cylinder with all three variables present. And when that happens, what's going on is that the rulings are not parallel to any of the three axes. Now, we won't work with these that often. So I did give you two examples here. This one is an oblique circular cylinder, which is in GeoGebra 3D. And the one on the right is an oblique parabolic cylinder. So let's take a look at these real fast. So again, oblique in this sense means tilted at an angle. So you can see the circle right there, but it is a cylinder, but it's not being drawn along lines that are parallel to X, Y, or Z, right? And so it's called an oblique cylinder. And in this case, the equation is going to involve X, Y, and Z. And if I look at the second one, this one is a parabolic cylinder. And again, you can see the parabola coming in right there. But when you look at it from the side, you can tell that it's being drawn along a line that is not parallel to any of the coordinate axes. Let's now take a look at another view. So this one right here is x squared minus 2z equals y. So you can see it's mentioning all three variables. And so we know that the rulings aren't parallel to x, y, or z, but this is an off-axis parabolic cylinder. And I plotted this one for you in CalcPlot 3D. So if you kind of tilt it up a little bit, you can see the parabola coming through, but notice that those lines along which it's parallel are not parallel to the X, Y, or Z axis. Now, be aware that 3D graphers are not perfect, all right? I use CalcPlot 3D the most often because it is one of the best out there. Wolfram Alpha also is very, very good. GeoGebra 3D actually had difficulty with the sine X cylinder. So the one that was Z equal to sine X, GeoGebra 3D graphed it as a two-dimensional shape. It did not give me the true shape of the sine of X equal to Z. This is what it should look like on CalcPlot 3D. So let's take a look at what it should have looked like, which is sort of, well, I don't know what you'd call that. It's a sine curve, right? So we have a sine curve right there, basically. And again, because it doesn't mention, this one is y equals sine x, so it doesn't mention z. So if I do Alt Z, I can see the sine function coming out, the bubble up, bubble down. I don't know, it's kind of like a magic carpet that's kind of wrinkled up a little bit, or a piece of bacon, a wavy piece of bacon. So when I'm looking at that one, keep in mind that sometimes these 3D graphers don't do a good job of graphing, in which case you need to use your brain and realize that you should be getting a three-dimensional object. It should look like these pictures down here. Now, when you go to Wolfram Alpha, which you can do by clicking on this link here, and if we want to graph y equals sine x, then it's going to open on a page that looks like this. It says 3D plot. Don't change that. Come down here. And what was it we were plotting? I think it was y equals sine x. So we just want to put in sine. I'm not sure if Wolfram Alpha requires parentheses around x, but CalcPlot 3D definitely does. So I'm going to do this. And now you can see that we've got the plot down here, and you can see that it is correct, that it is drawing a 3D image of it, right? So make sure when you plot these that it's meeting your expectation. Don't over rely on technology. We've talked about cylinders quite a bit, so let's shift gears and focus on quadric surfaces. Now, we have seen some cylinders that are quadric surfaces, like the hyperbolic one that we saw, and some that weren't, like the sine function and the cubic function. Again, to be a quadric surface, it has to be written in this form where A, B, C, D, all the way through J are real constants, but they could be zero. So it doesn't have to have all of these terms. But the highest power on the variable is 2, all right? So we've got x squared, y squared, z squared, xy, xz, yz, xyz, and a constant, possibly, all right? So when we take a quadric surface, and we intersect a quadric surface with one of the coordinate planes, the YZ plane, the XZ plane, or the XY plane, the trace of it is a conic section. Now, you may remember from earlier in your math career that a conic section could be a point, a line, a parabola, an ellipse, a circle, or a hyperbola. All right, so when we're looking at the trace of a quadric surface, its trace in each of the three coordinate planes is one of these. It's a conic section, most likely a parabola, circle, ellipse, or hyperbola. Now let's take a look at the first type we want to discuss, which are called ellipsoids. Now, ellipsoids are based on ellipses, and they include spheres, since circles are special cases of ellipses. So it includes spheres. The general equation for an ellipsoid is going to be x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Now, if a squared, b squared, and c squared are all the same number, it's a sphere, right? And that would be the radius squared. So when we're looking at this, this one is, of course, centered at the origin, 0, 0, 0, but I could have x minus 1 quantity squared, and then it would be shifted on the x-axis by 1. To see the trace in each of the three planes, what you do is you set the missing variable to be 0. For example, if I want to know what the trace of an ellipsoid looks like in the xy plane, in the xy plane, z is not present, so z is 0. So I would take this third term here on the left and wipe it out. And then I would graph x squared over a squared plus y squared over b squared equals 1. If I wanted to know what it looks like in the YZ plane, x is 0, so I would wipe out the first term and I would graph y squared over b squared plus z squared over c squared equals 1 in the YZ plane. Remember, when you're graphing in the coordinate planes, if z is present, it's always the vertical axis. All right. Now, for me, drawing a 3D image on a flat piece of paper is just not a skill that I have. It's best left to artists, so I'm going to use 3D graphers in the images and the lecture notes. So here's an ellipsoid. We know it's an ellipsoid because we have x squared, y squared, z squared. It's equal to 0, and we have 4, 9, and 16. So again, going back up here, except that should be a 1. How did I get that equal to whatever? Okay, I have an error there. Not good. Okay, so I'll have to fix that later. So this should be x squared over 4 plus y squared over 9 plus z squared over 16 equals 1. Okay, and that will give us an ellipsoid. All right, so let's take a look at this ellipsoid right here. All right, so here's our ellipsoid, and it is equal to 1. You can see right here in the equation. Now, how did I get CalPlot3D to plot it? Click on Select and choose Implicit Surface. We're graphing an entire equation, and we're not solving for any particular variable, so I just plot an implicit surface, and then I enter the equation I want to plot right here. Make sure you're out far enough to get the whole thing, because if you're in too far, you're only going to get part of the ellipsoid. So do you see how I only have part of it here? So I need to zoom out by clicking on the negative magnifying glass. Now let's talk about the traces of an ellipsoid. The traces of an ellipsoid are always ellipses. That is not always the case for other quadric surfaces, but it is true for an ellipsoid. So let's take a look at what it would look like in, say, the XY plane. In the XY plane, you can see that I have an ellipse, which is going between, well, it's kind of hard to tell, but it looks like between -3 and 3 and 2 and -2. And this is the XY plane. So you can see this right here. Now, how would I get that coming over here? So if I'm looking in the XY plane, what I'm going to do is I'm going to eliminate this term right here, z squared over 16, because in the XY plane, z is 0. And I'm graphing that, which goes, of course, between -2 and 2 along the x-axis and -3 and 3 along the y. Now, if I want to take a look at what the trace would look like in the XZ plane, then y is 0, so that would go out. So it still goes between -2 and 2 on the x-axis, but now between -4 and 4 on the z-axis. And you can see this one right here. Now let's take a look over here. If I want to see it in CalPlot 3D on the XZ, then I need to take out y, so I do Alt-Y. And now you can see it goes between -2 and 2 on the x and -4 and 4 on the z. And these are what are called traces. Now, when we do this, we're always going to get an ellipse for an ellipsoid, but that is not necessarily what we're going to get for other traces, right? Let's talk about paraboloids. A paraboloid is based on a parabola, as you might expect. It has one axis of symmetry, but it has no center. An ellipsoid truly does have a center, right? It's got a center of that elliptical three-dimensional space. So it's got a center, but a paraboloid doesn't have a center. It does have an axis of symmetry, but not a center of symmetry. So there are two basic types of paraboloids. We have elliptical paraboloids and hyperbolic paraboloids. And as you might expect, one is based on ellipses, which includes circles, and the other is based on hyperbolas, but they are parabolas in some sense. So in an elliptic paraboloid, the trace in one plane is an ellipse. Now this will be the plane given by the two squared variables. So the equation of an ellipsoid has two of the variables squared on one side of the equation, the unsquared variable on the opposite side. So in this case, if we were given the plane, the axis of symmetry is the z-axis in the first one because it's not squared. In the second one, the y is not squared, so the axis of symmetry is the y. And in the last, the x-axis would be the axis of symmetry because it's not squared. So if we take the plane of the two squared variables, like the xy plane right here, it will look like an ellipse. The difficulty is when we do that, I have to specify what level it's at because the shape of the ellipse changes as it moves along the line of symmetry. So let's take a look at one so that we can kind of get a feel for what it looks like. So here's an example right here. So let me close that one out. And you can see the ellipse right here, right? So what do I mean by you have to give the value of z to know what the shape of the ellipse is? Well, as it goes along the line of symmetry, which is the z-axis here, the unsquared variable, the ellipses get larger and larger as I move along that axis of symmetry. And because of that, that means that I would have to specify z equals 5 in order for you to know how big the ellipse is when z is 5, right? So it would be like, taking a cross section right here or something like that, right? So you can see this shape here. Now, if I wanted to look in the XY plane to see the ellipse part, I would do Alt-Z. And now you can see the ellipse on which it's based. But again, the ellipses change in size depending on what Z level I'm at. Now, what does it look like in the other two coordinate planes? So I've taken Z out, so let's take out Y. Oops, wrong key. And you can see it looks like a parabola, right? So this is an elliptical paraboloid. So on one of the traces, the one where the two variables are squared, it looked like an ellipse. And I took out Y, let's take out X now. If I take out X, it's still a parabola, but a different shape. So you can see that by taking one out at a time, you get the other two traces. So an elliptical paraboloid, two of the traces are parabolas, one of them is an ellipse, right? If you're evaluating the trace in the plane that gives the ellipse, remember you have to specify what the Z value is so that you know what it's equal to. It gives an ellipse of a different size. If you're eliminating one of the other variables, it gives you a parabola and you don't need to specify the Z value. It's always going to give you the same shape. Now, I do want to warn you in the textbook on figure 2.84 in one of the examples, in part C and D, they forgot to change the labels on the axes from X and Y to X and Z and Y and Z. So they're incorrect. So be careful and watch out for that. Let's now talk about a hyperbolic paraboloid. So we saw that with the elliptical paraboloid, in one of the traces, it was an ellipse and the other two were parabolas. Let's take a look now at what a hyperbolic paraboloid would look like. And a hyperbolic paraboloid, it again has two squared variables, but they're not added together like they were in the elliptical. As you might expect, in the hyperbola, you have opposite signs. So we have opposite signs here. So we have all different possible combinations, 6 different possibilities. When we're looking at these, the axis of symmetry, it does have one, is again going to be given by the unsquared variable. So if z is not squared, then the axis of symmetry is along the z-axis. Now, the trace in the plane without the variable around which it is symmetric gives us a hyperbola. So that sort of should make sense to you that you would get a hyperbola if you were to graph these. This time, however, because they have opposite shapes, it's giving that hyperbola and not a parabola. But weirdly, the hyperbolic paraboloid in the other two traces does give a parabola shape. So we've seen the elliptical parabola has one ellipse and two parabolas as traces, and the hyperbolic paraboloid has one hyperbola and two parabolas as traces. The hyperbolic paraboloids remind me of a saddle, like for riding horses, or a Pringles potato chip. So let's take a look at what one of those looks like so that you can kind of visualize it. So let me close out that hyperbolic or elliptical one. And you can see it right here, right? Now, the difficulty, of course, is that if we're going to get the hyperbolic one, we have to specify at what z level we're getting it. So that would be taking the z out. So I do Alt Z. And it's very difficult in CalPlot 3D to see the hyperbolas. You kind of have to visualize that it's these rulings that are coming down like this and like this. Each one of those shapes is a hyperbola at a different value of z. And then if I take out the other two variables in turn, I get, of course, parabola shapes, all right? So you can see them right there. And it does sort of look like a saddle or a Pringles potato chip, if you think of it that way. And you can spin it if you like, all right? And again, I graphed this as an implicit surface, all right? So that was the example of this one right here. And again, if you want to get the parabola, the hyperbola part, you have to set the level of z. If you want the two parabolic parts, then you're either wiping out the x squared term or the y squared term, and you don't need to specify the level of z. And example, oh, and here are the traces. So you can see the traces right here, graphing the different equations. In GeoGebra, I graphed the same one for you, but I actually outlined the intersection at a particular z level so that you could see what the hyperbola looks like. So when you're looking at this, this is just one level of z. And at that one level, the blue forms a hyperbola. And at a different level of z, I would have a hyperbola of a different shape, right? Let's take a look at example 11. In example 11, you can tell that this is a hyperbolic paraboloid. It's sort of been turned on its side if you would consider z to be up. This is x squared minus z squared equals y over 2. And so again, if we look at this one out here on CalPlot 3D, when we eliminate the y variable on this one, it's hard to see the hyperbolas, but basically, if you can visualize these lines here and here are forming hyperbolas coming out from the center. And if we get rid of the other two, I get rid of the x or I get rid of the z, you can see the parabolas coming through. Now we have two basic shapes left to discuss, which are hyperboloids. Now, hyperboloids, oddly enough, are not really what you expect. You expect something sort of hyperbolic, and they are hyperbolic. It's just, for some reason, to me, when I see the three-dimensional surface, I don't think of the hyperbola equation exactly at first. I have to sort of be trained to see where it's coming from. Hyperboloids are different from ellipsoids and hyperbolic paraboloids or elliptical paraboloids in that they have all three variables squared. But when they're written on the same side of the equation, two of the variable terms have the same sign and one of them has the opposite sign. So we generally write it so that we have the two variables with the same sign on the same side and the one without the same sign on the opposite side. So it looks like they're all positive, but of course, you know better. All right, now it will be symmetric about the axis where the variable that we've solved it for. They do have a trace, which represents a hyperbola. In fact, this time they have two of them, but it's not in the plane, which eliminates the variable around which it's symmetric. Instead, we keep that variable and we eliminate the other two one at a time, and that will give us the traces. The remaining trace consists of ellipses, oddly enough, of different sizes at different levels of the opposite sign variable. There are two basic types. There's a hyperboloid of two sheets and a hyperboloid of one sheet. So let's start with the hyperboloid of two sheets, which looks like this shape right here. All right, so when written on the same side of the equation, notice that two of the squared variables have the same sign. In the first one, they're both negative and the z squared term is positive. And the second one, the x squared and z squared are both negative and the y squared is positive, and then the last has the remaining option. And this gives us hyperbolas of two sheets. Now, when we're looking at this, the equation is set equal to 1, all right? So it sort of looks like two sun hats turned back to back and spaced apart. So when we're looking at it, we get the hyperbolic shape. If you want to visualize the hyperbolic shape, let me try to do one of them for you here. There's one, and there's the other. But I could have another one, which is coming along like this and like this. So you can see that I do have that hyperbolic shape in there, that hyperbola. So this one is negative x squared divided by 9 minus y squared divided by 4 plus z squared divided by 16 equal 1. So we'll be symmetric about the z-axis, and we can see it does look like two sun hats sort of back to back. So let's take a look at this out here. And again, if you don't like the box, you can click B when you're clicked in, and you can see the shape right here. Now let's take a look at what the traces look like. So again, in order to see the traces, you're going to eliminate one variable at a time by clicking the Alt key, holding it down, and clicking one of the others. So I eliminated the Z, which is the one it's symmetric about, and you can see that this generates different sizes of ellipses based on what height of Z I'm at. Now the other two will generate hyperbolas, right? Looking like this. Okay. Now let's go ahead and take a look at the traces. So again, to find the trace in the XZ plane, we take off the term that has the Y and we plot this hyperbola, right? So this is what it looks like. We saw these just a moment ago. And to plot the trace in the YZ plane, we take out the variable term that has X in it, and that will give us the other hyperbola trace. And the other one would be ellipses. Now let's talk about hyperboloids of one sheet. Now, in a hyperboloid of one sheet, we again have two squared variables with the same sign and one without. But in this case, it's going to be very similar, but in this case, we've got opposite signs. So these actually, when we say one sheet, we mean they're connected. So when we say they're connected, what we're looking at is actually the shape of a nuclear power reactor. It is, in fact, an exact hyperboloid of one sheet. So this is what they look like. All right, this is the hyperboloid of one sheet. And let's analyze these equations and see how they're different from the hyperboloid of two sheets. In the two sheets, notice that the two variables that had the same sign were both negative, and the one that it was symmetric about was positive, and this time the signs are reversed. So in a hyperboloid of one sheet, the two squared terms that have the same sign are positive, and the one that it is symmetric about is negative, all right? So this will produce a hyperboloid of one sheet. And let's take a look at what one of these would look like over here, right? So we can see that right there. This is our hyperboloid of one sheet. And in this case, x squared and y squared are both positive and z squared is negative. And so it's symmetric about the z axis. And if we want to examine the traces, let's take z out first. And we get ellipses at different heights of z. So the traces are ellipses. You have to specify what z level they're at. And then if we take out one of the other two, we'll get hyperbolas of different shapes, all right? And again, the hyperbola shape is like here. You can see the lines in CalcPlot 3D if you look closely enough. You can see the hyperbola shapes coming through. So this is example 13. This is a hyperboloid of one sheet. It is connected. How do I know that? X squared and z squared are both positive. Y squared is negative. It's equal to 1. All right. So I know it's a hyperboloid of one sheet. Now it looks a little bit different because I'm not zoomed out far enough for it to have a better shape. I'm not seeing all of it. So if I were here and I wanted to zoom out a little bit more, it would get more of that typical shape that you see. The last type that we want to talk about that's a quadric surface would be a cone. Now, when we think of a cone, we're actually only visualizing half of a cone. A double napped cone has a funnel shape on top and on bottom. It has a point, which is the vertex where the two funnels meet, and it has an axis of symmetry, which runs through the center of it. And it has a line, which you can see visualized here in pink, along the edge that generates it by swinging around in a circle like this. And it generates a double napped cone. What we typically think of is half of a cone, which is just one nap of it, which looks like a waffle ice cream cone right here. So when we're thinking about a cone, we should be thinking about the double napped cone. And we'll see how we can get just half of one if we want to. Now, these are fairly easy to produce. All three variables are squared as they were in the equation of a sphere. There's no constant term, however, and when written on the same side of the equation, two of the three variable terms have the same sign and one is opposite. So these look like this, all right? This right here. Now, how is this different from the hyperboloids? When we go back to the hyperboloids, remember that the hyperboloid formula had a constant term of 1. That's how they're different. In the cone formula, there's no constant term of 1, right? So we do have two variable terms with the same sign, one without. Right? The variable in the squared term that's isolated, that has a different sign, that's the one about which the cone is symmetric. All right. So let's take a look at what these look like when we go to graph them. Here's one. Now keep in mind that the cones don't have to be based on a circle. They can be based on an ellipse. And this is an example of an elliptical cone that you see right here. You've got x squared over 4 plus y squared over 16 equals z squared over 9. It's got to be symmetric about z because z is isolated. And in that case, that means if you want to see the trace in the xy plane, you need to specify at what level of Z, and it's going to give you ellipses of different sizes. If you want to look at what it looks like in the XZ plane, then you take out the Y variable and so on. So let's take a look at what this one looks like. So here it is right here. And you can see the ellipses if I do it right here. You may be saying, well, I'm not seeing all of it. It looks like it's cut off. Well, it is cut off. If I zoom out a little bit, I'll see a little bit more of it. It's taking a long time to graph, right? But again, that's because I'm not showing you all of it, right? And so when we're looking at the cone, we have different shapes that we can visualize. Now, when we come to look at the cone and we do the traces, so if I take out the Z, I'll see those ellipses of different shapes. I have to specify what Z level. If I look at the other, take out X or take out Y, I still see the cone shape, right? So 2 of the traces are still cones. 1 of the trace are ellipses at different heights. So how do we get the shape of an ice cream cone, just 1/2 of it? What we do is we solve for the variable that it's symmetric about, the one with that's isolated on one side by itself, and then take the square root of it. And that will give us just 1. So the positive square root would give us the one in the up, right, or forward direction, and the negative square root would give us one in the down, left, or back into the screen direction. Right? So here's an example of one where I took a double napped cone equation right here. I solved it for Z squared and then took the square root and the positive square root because it's symmetric about Z. If I take the positive square root, it'll be opening up. If I had taken the negative square root, it would open down. And we can take a look at what this one looks like out here on CalcPlot 3D by closing up that screen. And you can see this one right here. And then if I wanted the one that opens down, what I need to do, and of course, CalcPlot 3D is not graphing all of it. That's why it's cut off a little bit at the edge. If I put a negative at the front and then I have to hit enter to get it to plot, you can see that it gives me the downward opening one. So we have reached the end of what we wanted to talk about in this section where we were talking about cylinders and quadric surfaces. We'll be dealing with quadric surfaces and cylinders quite a bit in the days and weeks to come. So I hope you'll join me for the next video where we talk about cylindrical and spherical coordinate systems. You've already talked about polar coordinate systems in a previous course. Now it's time to talk about 2 coordinate systems that pull us into 3 dimensions. I hope to see you there.